Ceres should be a dead rock. It is 588 miles across, frozen, airless, and buried between Mars and Jupiter where nothing interesting is supposed to happen. For 2 centuries, it was a featureless point of light, discovered in 1801, classified as a planet, then demoted, then reclassified, catalogued, and largely forgotten. When the James Webb Space Telescope turned its instruments toward Ceres in early 2025, the scientists running the program expected to confirm what they already knew. They expected a routine measurement. What came back was not routine. And the detail that made it strange is the kind that does not get simpler the longer you look at it. Start with what everyone agrees on. Ceres lives in the main asteroid belt. It is the largest body out there, round enough to have pulled itself into a sphere under its own gravity, which already tells you something. It is big enough to behave like a world, not just a rock. Surface temperature hovers around -100 degrees Celsius. No real atmosphere, no moons, no reason, by most classical models of the inner solar system, to be anything other than a cold, dead remnant. That was the textbook. The textbook was not wrong. It was just too small for what was actually there. The first sign that Ceres was more complicated than it looked did not come from a spacecraft. It came from a telescope pointed at it from 250 million miles away. In January 2014, the ESA's Herschel Space Observatory, an infrared telescope operating in a region of the spectrum that ground-based telescopes cannot access, detected water vapor rising from Ceres. Not a trace, not an artifact. A clear spectral signature, confirmed multiple times, at a rate of roughly 6 kilograms per second. Picture that. A body with no visible atmosphere, no liquid surface, and a temperature cold enough to freeze carbon dioxide, quietly venting water into space at the weight of a grown person every single second. The vapor appeared when Ceres swung closer to the Sun in its 4.6-year orbit, and faded when it moved away. The first instinct was sublimation. Sunlight warming surface ice directly into vapor. No liquid involved. The same process that gives comets their tails. Simple, tidy, closed. But the water didn't come from where that model expected. In 2015, NASA's Dawn spacecraft arrived at Ceres after a 4.3 billion-mile journey. What it found on the surface stopped the science team cold, not figuratively. There were 130 bright regions scattered across the surface, the most striking of them clustered in the floor of a 57-mile-wide impact crater called Occator. These spots were so reflective they had been visible from Earth before any spacecraft got close. From orbit, they looked almost fluorescent against the dark, dusty terrain. The first explanation was ice. Clean surface ice, exposed by impacts, reflecting sunlight back like mirrors. That should have been the end of it. It was not. Dawn's spectrometers identified the bright material as sodium carbonate, a mineral salt, not ice, the kind of salt that forms when mineral-rich water evaporates and leaves its dissolved contents behind, the same way you see white crust ringing a dried-up saltwater lake on Earth. Which meant the bright spots weren't just exposed ice. They were the dried stain of water that had once been liquid. Liquid water means temperatures above freezing, even briefly. It means chemistry. It means the interior of Ceres, at some point, had been warm enough to dissolve rock into brine and push it upward toward the surface. A frozen rock. With an ocean. The scientists pushed further. In Dawn's final phase, engineers adjusted the spacecraft's orbit until it was skimming just 22 miles above the Ceresian surface, close enough that the gravity measurements it returned allowed researchers to build a picture of what lay underneath. Beneath Occator crater, roughly 40 kilometers down, the data suggested a reservoir of brine. Salty, mineral-laden water, or at least something close to it. The reservoir appeared to be roughly 400 kilometers wide, broader than the state of California. And the crater sitting above it, the impact that fractured the crust and gave that brine a path to the surface, was dated at approximately 20 million years old, geologically recent. The bright salt deposits on the floor, the ones so vivid they had puzzled astronomers for decades, were dated even younger, approximately 4 million years old. Think about what 4 million years means. If you compressed Earth's entire 4.5 billion year history into a single calendar year, 4 million years ago falls in the last 10 minutes of December 31st. These deposits are not ancient scars. They are nearly brand new. The simple explanation shifted, no longer just sublimation. Now, an ancient ocean, long frozen, leaving its chemical traces behind as the last of its liquid slowly cooled into solid. A relic, a record, something that had happened and was now over. That version made sense, closed the loop, filed Ceres under interesting but inactive, and moved on. Then one more detail came back from Dawn's instruments, a mineral called hydrohalite, a specific form of water ice mixed with sodium chloride that only exists when temperatures are near freezing, rather than the deep cold of Ceres's outer surface. Hydrohalite is unstable. Once exposed on the surface of a near-vacuum body like Ceres, it disappears in roughly 100 years. Not 1,000 years. Not 1,000,000 years. 100. It breaks down into ordinary sodium chloride and vanishes. It was still there. That means the brine is not a relic. Something has been pushing it to the surface recently enough that this unstable mineral has not had time to decay. And recently, in this context, means within the last century at most. Something beneath Okator crater is still moving. Not ancient, active. The simple explanation got you halfway. Halfway is where this becomes uncomfortable. By the time the 7 Nature papers landed in August 2020, the scientific classification of Ceres had formally shifted. Not an asteroid, not just a dwarf planet. An ocean world, the same category applied to Europa, orbiting Jupiter under a shell of ice with a global subsurface ocean driven by tidal heating. The same category as Enceladus, Saturn's small moon that vents geysers of ice and water into space, and has become one of the most discussed candidates for extraterrestrial chemistry in the solar system. Ceres, sitting in the asteroid belt between Mars and Jupiter, with no gas giant pulling at its interior, no tidal driver, no obvious source of internal heat, was now formally sharing a classification with the solar system's most compelling targets. The scientists behind the classification were careful. They noted that ocean world status does not require a global ocean, only that liquid water exists or has existed in significant quantity in the interior. And they noted that the current state of the brine reservoir was uncertain. Whether anything was still liquid, or whether the whole system had frozen to slush, remained a live question. The data from Dawn could not fully resolve it. But something was reaching the surface, something warm enough, or pressurized enough, or saline enough to defeat the cold. Here, the second version enters, and it requires going further back than Okator crater, further back than Dawn, further back than Herschel. It requires asking where Ceres actually came from, because in early 2025, the James Webb Space Telescope looked at Ceres, and what it saw in the infrared fingerprint of that rock, the first time any instrument with Webb's precision had read Ceres at these wavelengths, was not what you would expect from a body that formed where it lives. It was something older, something that didn't belong this close to the sun. That is where this becomes a different kind of story. If the brine is still rising, what is keeping it warm? And if something is keeping it warm, in a body this small, this far from any tidal driver, This long after the solar system's early heat should have faded. For how long has that been true? The James Webb Space Telescope does not take pictures of Ceres the way Dawn did. It does not produce crater maps or surface images. What it does is read light, specifically infrared light at wavelengths between 2.5 and 5.3 micrometers, a range that Earth's own atmosphere absorbs so completely that no ground-based telescope can see through it. This is the window where water chemistry is written, where minerals formed by liquid water leave their signature in the spectrum, where the difference between a rock that was always dry and a rock that was once soaked becomes legible. Ground telescopes cannot reach this window. Webb can. When Rivkin and colleagues published the first JWST-NIRSpec measurements of Ceres in January 2025, the spectrum came back with strong absorptions centered near 2.72 micrometers. Magnesium-rich phyllosilicates, minerals that form through prolonged contact with liquid water, the kind of chemical alteration that requires time, temperature, and sustained wetness to produce, consistent with what Dawn had found globally. But there was something else in the spectrum, centered beyond 3 micrometers, that sharpened a question the Dawn data had left partially open. Ammoniated minerals, specifically ammoniated phyllosilicates. This is the detail that does not fit the address. Ammonia ice is not stable this close to the Sun. Solar radiation destroys it over geological timescales. If Ceres had formed where it currently orbits, the working assumption for most of the 2 centuries astronomers spent watching it, the ammonia signal should not be there. It should have been destroyed billions of years ago, leaving no trace. The fact that it remains locked into the crystal structure of the surface minerals is a chemical record, a record that points not to the asteroid belt, but to somewhere much colder and much further out. Webb saw it. The spectrum did not fit the address. There is a well-supported model called the Grand Tack hypothesis, Jupiter and Saturn migrating inward toward the Sun, then reversing outward during the first few million years of solar system history. That migration scattered bodies from the cold outer regions, where ammonia ice was stable and water was abundant, into the main belt. Ceres, on this version, did not form where it lives. It formed somewhere beyond Jupiter's current position, was displaced inward by the planetary reshuffling of the early solar system, and has been sitting in the asteroid belt ever since, carrying a chemical fingerprint that belongs somewhere else entirely. Physical samples returned from asteroids Ryugu and Bennu showed the same spectral signature Webb found on Ceres, the same heavily water-altered minerals, the same absorption patterns. Both bodies are now suspected to have formed in the cold outer belt before migrating inward. Japan's Hayabusa 2 brought back Ryugu samples in 2020. NASA's OSIRIS-REx brought back Bennu samples in 2023. The same fingerprint, appearing across 3 bodies in 3 separate investigations, is no longer a coincidence. It is a pattern. But migration explains the ammonia. It does not explain what is still moving beneath Okator crater. In 2025, researchers at JPL ran thermal and chemical models of Ceres's interior using everything Dawn had measured: composition, internal structure, gravity profile, mineral distribution. What they found was that Ceres may have had a sustained, long-lived source of chemical energy. Reactions between water and rock called serpentinization, which produce hydrogen as a byproduct. On Earth, hydrogen fuels microbes in the deep crust and on the ocean floor, far from sunlight, where chemistry, rather than solar energy, drives life. The models suggest this process may have persisted inside Ceres for an extended geological time frame, not the brief warmth of early radioactive decay, but something longer. This is not confirmation of life. What the models confirmed is the chemistry. What they cannot confirm is whether anything was there to use it. Here is the detail most people skip. When Dawn ran out of fuel in November 2018 and went silent, the mission team placed it in a long-term orbit designed to prevent surface impact for at least 20 years. The reason? Planetary protection. The same protocols applied to Europa and Enceladus, the solar system's most carefully guarded potential ocean worlds, were applied to a 940-kilometer body in the asteroid belt. Dawn was quarantined above a world the data suggested might require that level of caution. A spacecraft built for routine science, now orbiting in permanent silence, above a surface where the bright salt deposits in Okator are less than 4 million years old, and something 40 kilometers below may still be moving upward through fractured rock. The strongest version of this story accounts for all of it at once. Ceres is a preserved fragment of the outer solar system, displaced inward by planetary migration billions of years ago, still geologically active at its surface, possibly still mobile in its interior, formally classified as an ocean world by the consensus of 7 peer-reviewed studies. Webb's 2025 measurement did not overturn that picture. It deepened it. The ammonia fingerprint is not a contradiction of what Dawn found. It is the explanation for how Ceres came to have what it has, how a body with no tidal driver and no gas giant neighbor managed to hold on to enough water, long enough, to do something with it. But the strongest version still leaves the largest problem open. Whether the brine is still liquid, still capable of the chemistry the models suggest, that cannot be answered from orbit. Webb reads surface mineralogy from 1.5 million kilometers away. It cannot see 40 kilometers underground, and there is no funded successor mission, no lander, no subsurface probe, no planned follow-up to the 7 Nature papers, to the JWST spectrum, to the 2025 habitability research. The body it describes is still drifting, still exhaling its chemical record toward the surface at intervals no one fully understands. Here is what that means. Ceres has no tidal heating, no gas giant proximity, no geological youth. Every condition planetary science has pointed to as a prerequisite for liquid water in the inner solar system, Ceres has none of them, and yet it qualifies. If the threshold for ocean world status is achievable by a 940-kilometer rock in the asteroid belt with no obvious energy driver, then the assumption that liquid water here requires exceptional conditions is not a physical law. It is a convenience we invented before we had instruments precise enough to check. In the same JWST study, the instrument also observed Hygeia, the 4th largest body in the main belt, 1/10 the mass of Ceres. Its spectrum showed the same fingerprint, the same absorptions, the same chemical signature. The researchers noted this implied Hygeia may have undergone similar processes, similar histories. If that holds, the question is no longer about Ceres alone. It is about every dark object in the belt we have never looked at, in the wavelengths where water chemistry is written. There are millions of them. Webb looked at Ceres. It expected to confirm a catalog entry. What came back was a chemical fingerprint identical to the most water-processed material humanity has ever physically held. Samples from Ryugu and Bennu, bodies that formed in the cold outer solar system before something pushed them inward. Ceres is not what it looks like. It never was. Ceres, 940 kilometers across. Surface temperature minus 100 degrees Celsius. Something may still be moving through fractured rock, 40 kilometers below Okator crater. Dawn is still up there, orbiting in the dark, quarantined above a world it proved might require protecting. The bright spots in the crater floor are less than 4 million years old. The brine that made them may not be done. No mission is planned. No one is going back.